today, as Shamno mentioned, the title of my talk is a topologically rigid set of quotients of the Davis complex. If those words don't really make sense, that's okay. I'm going to try to define them all. So first, I wanted to talk about topological rigidity. So topological rigidity is part of a class of rigidity statements. So basically a rigidity statement, if you're not familiar, these statements all have the characteristic that a weaker assumption implies a stronger assumption. So there's some very famous rigidity results. For example, you've probably heard of Mostel's rigidity. And there's quasi-isometric or QI rigidity. That's something that I think Shandong has worked on. And also there's marked length spectrum rigidity, which I'm currently working on. So there's like a collection of rigidity. I guess like there's different kinds of rigidity that you can explore. But today we're going to be talking about one special kind of rigidity called topological rigidity, which is defined for a class of topological spaces. So first, I'm just going to define topological rigidity. So we say that C is topologically rigid if for all X and X prime in C, an isomorphism on the level of fundamental groups induces a homeomorphism. So in general, as you probably already know, if two objects have the same fundamental group, most likely than not, they are not homeomorphic. So for example, if you're taking algebraic topology, you probably have seen that a genus one surface of one boundary component and a wedge of two circles have the same fundamental group, which is the free group on two generators, but they are in fact not homeomorphic. So having isomorphic fundamental group is much weaker than being homeomorphic. So that's why it's a rigidity statement. And it's actually pretty hard to find examples of topologically rigid spaces. But there are a few famous examples. So yes, so I guess first of all, before I do that, I guess I should maybe state my end goal here. So my end goal is to talk about a theorem that I proved. So the theorem is that there exists an infinite class of Davis orbit complexes along with their finite shaded covers that is topologically rigid. So that's what I guess the key idea of this talk is. So I'm going to define what a Davis orbit complex is, but if you don't know what these are for now, you can just think of them as KG1 spaces of right angle Coxeter groups. So a KG1 space means that the fundamental group of that space is the right angle Coxeter group, and the higher homotopy classes are trivial. So that is my final result. But in order to build up to that, I need to sort of motivate the result and also give some definitions. Okay, so first, I'm going to give some examples of topologically rigid spaces that you might care about. So there's a classical result. which is the set of closed two manifolds. It's topologically rigid. And as you probably know, the fundamental group of a closed two manifold or a closed surface is determined by the genus number. And the genus number, because of the classification of surfaces, is enough to give like a homeomorphism classification. So this is a classical result. And there's also a very famous result, the set of simply connected and closed three manifolds. So this was actually proved by Perelman, and he won't take full credit for it in Hamilton. So Perelman used Ricci flow developed by Hamilton to prove this theorem. This is also known as the Poincare conjecture. So that's like a very famous problem. And yeah, so there's like some other pretty impressive results as well. The set of closed aspherical non-positively curved manifolds of dimension greater than or equal to 5. So this was proved by Farrell and Jones. There are a series of papers in the 80s and the 90s. And yeah, basically aspherical, if you're not familiar, that means that pi 1 of the topological space is non-trivial. But pi n of x is trivial for n greater than or equal to 2. And if the topological space has a CW complex, then an equivalent condition is that the universal cover is contractible. So that's what aspherical means. And this is actually part of a very famous conjecture. So there's a famous conjecture that is still open. So here's an open question. It's called the Boreal Conjecture. And the Boreal Conjecture claims that the class of aspherical closed manifolds of all dimensions, of any dimension, is topologically rigid. So this is a long-standing conjecture that is still open, if that's something that interests you. Yeah, so this is the result by Farrell and Jones is a special case of the Boreal conjecture. So those are just some famous sets of topological spaces that are topologically rigid. What I work with is a little bit different. But before I go on, I also want to point out that, okay, so there's these 3 examples, and this is a special case of the Boreal conjecture. But we also have some local results. So for example, Shandong proved in 2006 that the set of quotients of Fuchsian buildings by an action of a co-compact lattice that is also a topologically rigid set. I just wanted to mention that in case you wanted to ask him about it. So that's like a local result. And then there's also Lafont. So Lafont has a result with hyperbolic key manifolds, which I'm not going to define just yet, but I wanted to mention this result because it is actually important in what I proved. It was a key tool. And to give you an idea, the P there stands for piecewise. So these are these are topological spaces that are homeomorphic to, I guess, like objects with piecewise Riemannian metric. So yeah, so I'll talk a bit more about those later, but that's just sort of a preview of the spaces that we're interested in, or that's just like a preview of sort of like spaces that people are interested in that happen to be topologically rigid. So that's sort of an introduction for topological rigidity. But I also wanted to sort of talk about my motivation for studying topological rigidity, which is actually a little bit different than like the motivation of the people that I have just cited. So my motivation is that there's an open question, which is find the abstract commensurability, write that a bit neater, abstract commensurability classes of right-angled Coxeter groups. So I'm going to define that next. So abstract commensurability is something that geometric group theorists often look at. So basically, two groups are abstractly commensurable if they have isomorphic finite index subgroups. And this is actually crucial for studying quasi-isometric rigidity. To study QI rigidity, you need to find abstract commensurability classes. So that's what actually initially led me to this problem. So trying to find abstract commensurability classes for right-angled Coxeter groups. And I'm just going to say some stuff mainly for the experts, which is that one common strategy for finding abstract commensurability classes is to take topological spaces whose fundamental groups are the groups that you're looking at and construct finite Shia covers that are homeomorphic. And sometimes it's really hard to figure out if two things are homeomorphic or not. So but the fundamental group is a lot easier to compute. So it's easier to work with topologically rigid spaces when you're studying abstract commensurability. So that was just sort of like a short, I guess, like explanation of my motivation for studying topological rigidity. Yeah, so that kind of completes the first section of the talk. But next I wanted to move on to right-angled Coxeter groups. So I'm going to abbreviate these as RACGs. And they're basically a collection of groups that I've been studying for a while. So I'm going to define them. And I guess like the funny thing is that one of the first times I heard these defined was when Shandong visited Madison and gave a very nice mini course on them. So he's actually an expert on these, but I still wanted to define them in case you don't know what they are. So in order to define a right-angled Coxeter group, you need a simplicial graph. So we're going to call that gamma. So gamma is a simplicial graph. And basically what this means is that you're not allowed to have loops and you're not allowed to have two edges between two vertices. So it's just like a type of graph with some restrictions. And just some notation, E of gamma is going to be the edge set of gamma, and V of gamma is going to be the vertex set of gamma. So that's our setup. We have a simplicial graph and with an edge set and a vertex set. And we say that W gamma is a right-angled Coxeter group with defining graph gamma. If I'm just going to give the group presentation. W gamma is generated by elements of the vertex set. So the vertices define the generators. And in addition, we have this like right angle condition, which means that every generator is order 2. And also 2 generators commute if and only if there is an edge between them. So that is the group presentation of a right angle Coxeter group with defining graph gamma. And if you didn't quite absorb that, we can give some examples. So first I wanted to start out with just like a very simple graph. This simple graph is just 2 vertices. There's no edges between them. So we can try to write a group presentation. So I have 2 vertices. Those are my generators. And I have no edges. So the only relations are the that each generator is order 2. And that's it. And as you probably know, this is actually isomorphic to a free group where every element is order 2. So that's one example of a right angle Coxeter group. And another example is sort of the opposite end of the spectrum. And this graph is actually a huge headache for people who are working with QI rigidity for right angle Coxeter groups. If your defining graph has this complete graph, a subdivided complete graph on 4 vertices, that's actually been a huge obstruction for people in that field. But yeah, so this is a K4 graph, complete graph on 4 vertices. So there is a edge between every pair of vertices. And there are 4 generators because there are 4 vertices. Each one has order 2. And also there's a lot of commuting. Every single element commutes. So this group is abelian. So this is going to be an abelian group. And yeah, so just like sort of the opposite of the first example. So those are 2 examples of right angle Coxeter groups. And hopefully that gives you a flavor of how these things are defined. Okay. So now, if there is no questions, I just wanted to make sure that everything is clear so far. So once we define right angle Coxeter groups, we can move on to Davis orbicomplexes, which is the next topic. So in my title, what I have is quotients of the Davis complex. And I'm actually not going to define what a Davis complex is. So you can sort of think of it as, so it's what's called a model geometry for a right angle Coxeter group, which means that it's a space on which a right angle Coxeter group acts nicely, whatever nicely means. These Davis complexes are really of interest to people who are studying right angle Coxeter groups and Coxeter groups in general. But I'm not going to define them. Instead, I'm going to define these quotients, which are called Davis orbicomplexes. So first, I want to make sure that people know what an orbicomplex is. So an orbicomplex maybe I can write it this way. An orbit complex is a union of orbifolds identified along homeomorphic suborbifolds. Oops. So for those of you who don't know, an orbifold is sort of like a generalization of a manifold. So remember that for a manifold, every point is locally homeomorphic to Rn, but for an orbifold, you're actually allowed to have these like singularities, these cone points that are locally homeomorphic to Rn by an action of a finite group. So here's an example of what's called a teardrop orbifold, and you can have it looks like a manifold of cone points, and for like an orbit complex, you can just have like multiple orbifolds identified along homeomorphic suborbifolds. So that's a very bad drawing of an orbit complex. So yeah, so we're going to use a right-angled Coxeter group to define these Davis orbit complexes. So I'm just going to give an example of a construction of a Davis orbit complex. I'm not going to describe the construction in detail. I'll just give you an example to give you a flavor of how the construction works. And I should say that these Davis orbit complexes were actually developed by Danny Stark and Thomas in 2017. They wrote a paper about the, I guess, like abstract commensurability classes of right-angled Coxeter groups that goes in detail about these Davis orbit complexes and how they're constructed. So you can definitely reference that if you're interested. So basically, here's an example. I drew what's called a generalized theta graph. And a generalized theta graph consists of two vertices that are cut vertices and some number of edges between them. So this is an example of a generalized theta graph. And I think the reason they're called that is because if you have three subdivided edges and you rotate it, it actually looks like a theta. Yeah, so this is my defining graph. And then I can define a right-angled Coxeter group using that defining graph. And what I want to do is I actually want to construct a KG1 space for this right-angled Coxeter group. So the way you do it is that for every single branch, so the pink, red, blue, and orange, these are called branches. So you take one branch of your graph, basically a collection of valence to vertices and the edges between them. And these actually form a special subgroup of the right-angled Coxeter group. And you can build a Cayley graph of that subgroup. So if you build part of the Cayley graph, you kind of get this structure here. So remember that a Cayley graph, there's like an edge between each relation, or there's an edge of there's like a relation and there's like points for the group elements. So the way that I've drawn this Cayley graph makes it look like a cat zero structure. But you actually want to put a hyperbolic metric on that portion of the Cayley graph to get this two-dimensional orbifold. So this is a two-dimensional orbifold. And you can construct one of these two-dimensional orbifolds for every single branch in your defining graph. And then you have a collection of two-dimensional orbifolds, and then you glue them together along an edge. So there's like this edge between, in the Cayley graph, it would be like an edge between the two generators that are the cut points or the cut vertices. They're not cut vertices. Together, they're like a cut set, I guess. So they're like a cut pair technically. So you have this edge in the Kähler graph between two vertices and a cut pair, and these are the non-valence two vertices. So you glue that edge together, you identify all the orbifolds along that edge, and you get a orbit complex. So that is an example of a Davis orbit complex. So that's the object that we'll be working with. And I just wanted to state the goal again. So the goal is to find a set of right-angled Coxeter groups that I'm going to denote by curly W, such that the set of Davis complexes, Davis orbit complexes, D gamma associated with W gamma, along with their finite Shea covers. Is topologically rigid. So yeah, so that's my goal here. And I should state a result by Emily Stark, which in this paper was really the inspiration for my paper. This is in 2017. And she says that she found that let X be the set of finite sheeted covers of Davis complexes, orbit complexes associated with one-ended right-angled Coxeter groups. Make that a little bit bigger. So she found that if you just take all of the one-ended right-angled Coxeter groups, construct your Davis complexes, orbit complexes, and take their finite Shea covers, that set is actually not topologically rigid. And yeah, so this is not super, I guess, in a way, it's not super surprising because it's hard to get a topologically rigid set. But the surprising thing is that she only looked at when gamma is a cycle of generalized theta graphs. So I'm not going to explicitly define what these are, but I'll draw an example of one. So you have a theta graph, and I think I misspoke earlier. These are not cut vertices, but they're non-valence. They're vertices that are not part of a branch. So you have these two vertices and a bunch of edges that are subdivided between them. So that's a generalized theta graph. And you can sort of glue a bunch of generalized theta graphs together along their non-valence two vertices to make a cycle of these generalized theta graphs. So these are so Stark just like restricted to this specific set of graphs. And she found that even if you only restrict to right-angled Coxeter groups defined by these graphs that are one-ended, then their Davis orbit complexes and finite Shea covers are not topologically rigid. So yeah, so I actually drew out the example that she gave. So in her paper, she gave this example where this is the defining graph. It's a cycle of right angle. It's a cycle of generalized theta graphs, and then you can construct a Davis orbit complex out of that defining graph. And the other thing I wanted to point out is that there's a singular set. So I'm going to be referring later to a singular set of the Davis orbit complex, and that's what's highlighted in blue here. So this blue tripod here is called the singular set. And it's basically where the orbifolds are glued together. So this is her example of a defining graph and the Davis orbit complex associated with it. And she found some finite Shea covers of the same degree that are actually not homotopic. So I also kind of drew these out. So here are these finite Shea covers. Sorry, I'm just gonna move this up really quickly and then I'll zoom in again. So it turns out that if you take finite Shea covers of the Davis orbit complex, these covers are going to be, they're not going to be proper covers in the sense that Hatcher defines them in algebraic topology. They're actually branched covers, which means that there are singular points in the cover. Or also, I guess in this case, they're like orbifold covers. And yeah, so what these finite Shea branch covers look like is that they consist of these orbifolds that I actually call them jester hats because I think they look like jester hats. Like these like medieval court employees wear these hats. So these are basically orbifolds with some number of cone points with one boundary component. So the fins and the Davis orbit complex actually lift to these jester hats, and then the jester hats are glued to a graph. So the singular set, in this case a tripod, lifts to this graph, and the cycles in the graph are kind of glued to boundaries of the jester hats. So so that's what a finite Shea cover looks like. And she actually found two 16 Shea covers that are, so these are 16 shaded covers of the Davis orbit complex. And they are not homeomorphic because they're singular sets. These graphs are not homeomorphic, but they are in fact homotopic. So they're both homotopic to a 6-fold sphere with jester hats glued to them. So this is an example of a case where you have like just one fixed Davis orbit complex. This Davis orbit complex, along with its finite Shea covers, turns out to not be a topologically rigid set. So this example, I think, really illustrates that it's very hard to find a topologically rigid subset of these Davis orbit complexes and their finite Shea covers. So yeah, so that's like a major challenge. Even if you fix a single Davis orbit complex, there's no guarantee that its finite Shea covers are going to be homeomorphic. So that is what Stark proved. So I just wanted to sort of like give an example where topological rigidity fails. And now we can go on to the theorem again. And so just to remind you, since it's easy to forget things, so So, okay, I guess I'll write down the theorem again. There exists an infinite class of Davis orbit complexes along with their finite Shia covers that is topologically rigid. So I'm going to call this class C. So basically, just as a refresher, this means that for all x and x prime in my topologically rigid class, if I have an isomorphism between fundamental groups, then I have a homeomorphism between the topological objects. So that's topological rigidity. So that's, I should say that this is my theorem that I've been building up to. And yeah, so not only are there infinitely many Davis orbit complexes, distinct Davis orbit complexes in this class, but all of the finite Shia covers of these Davis orbit complexes belong to this topologically rigid class. But there are some restrictions because there's a lot of obstructions to topological rigidity. This is actually just the second half of my paper because the first half is talking about some obstructions to topological rigidity, and it turns out there are many obstructions. So in order to successfully construct this topologically rigid set, we really have to impose a lot of conditions. So I'm going to attempt to list out these conditions, but not in very precise terms, because I don't want this to be too technical in case I run out of time. So X is going to be an orbit complex that is a finite Shia cover of D gamma, where gamma is 3 convex and also not repetitive. Not going to really define these terms. But I guess like 3 convex is pretty easy to define. Basically every branch has at least 3 subdivisions. So remember that for my generalized theta graphs. Oh yeah, the other thing I want to sort of point out is that gamma is a cycle of generalized theta graphs. That's important. So for my generalized theta graphs, which I've drawn very small here because of space, remember that I have these like branches associated to them. So all of these branches have to have at least 2 vertices in them. And the reason for this is because this kind of ensures that the right angle Coxeter group is hyperbolic and also 2-dimensional, if you're familiar with what that means. And also you want these graphs to be non-repetitive. And this is a notion that I came up with in the paper. But basically it's a condition on the Euler characteristics of these generalized theta graphs. So there's like those 2 conditions, and we're also of course only looking at cycles of generalized theta graphs because that's what Stark worked with. And there's some more assumptions. First of all, X is homeomorphic to an orbit complex that consists of gesture hats glued to genus G surfaces with B boundary components. And and every boundary component of the surface has at least one gesture hat glued to it. So this is a very specific type of Davis orbit complex, or sorry, a very specific type of orbit complex. So for example, you want the orbit complex to be homeomorphic to, this is a very bad drawing, I apologize. You want this finite shade cover to be not homeomorphic, homotopic to a surface with boundary where every boundary component is glued to a boundary of a gesture hat. So that's one condition. And the second assumption is that the singular set of X has an easily computable complete graph invariant, which is a super vague statement. But basically what ended up happening here is that I use Laffont's topologically, so Lafont has this topological rigidity result for p-manifolds, for hyperbolic thick p-manifolds, which I didn't really define these, but you can just think of them as a bunch of hyperbolic surfaces glued together along simple closed curves. So you could have something like this. You could have multiple surfaces glued to a curve as well. So that's just an example of a hyperbolic thick p-manifold. So Lafont has this topological rigidity result I mentioned way in the beginning of this talk. And this result actually reduces, so my theorem reduces to a graph isomorphism problem. So basically, condition by assumption one, using assumption one, we are able to apply Laffont's topological rigidity result because it turns out that if my finite shaded cover of a Davis orbit complex satisfies assumption one, then there is a finite shaded cover that is a hyperbolic p-manifold. And as a result, I can use Laffont's topological rigidity result for p-manifolds to reduce this topological rigidity result for finite shaded covers of Davis orbit complexes to a graph isomorphism problem. So basically, if X and X prime have the same fundamental group, then that if and only if their singular sets are homeomorphic. And remember that the singular sets of these finite shaded covers of Davis orbit complexes are actually graphs. And how do you figure out if two graphs are homeomorphic? Well, one way to do it is to prove that they're isomorphic. And unfortunately, the graph isomorphism problem is not known to have a very low computational complexity. It's actually not known to be like solvable in polynomial time or NP complete. So that's kind of a challenge, which is why you need to restrict to sort of like a nice singular set with like an easily computable graph invariant. So I can sort of just do an example of the graph invariant. or maybe I could just define what a complete graph invariant is. So basically a complete graph invariant is the combinatorial tool for determining if two graphs are isomorphic. So an isomorphism between graphs is, the vertices in the edges map bijectively. And the complete graph invariant is something I call cycle count vectors. So basically, if I have a graph that is a cover of a singular set, so it's going to be, like, for example, I have this graph here. I have like a bunch of vectors, and there's like 2 force cycles labeled with 1 and 2 arrow. Sorry, there's 2 force cycles labeled with 1 and 2 arrows. So I have like a 2 here and a 0 here because there's 0, 8 cycles labeled with 1 or 2 arrows. And I have 1 8 cycle labeled with 1 or 2 arrows. So that's my second vector is 0, 1 because there's no force cycles labeled with 1 or 2 or 3 arrows, but there's 1 8 cycle. And finally, I have 1 8 cycle labeled with 1 or 3 arrows. So I also have a 0, 1 for x3. And so you can sort of define these cycle count vectors for the singular sets of this sort of like of these covers, finite shaded covers of Davis orbit complexes. And I kind of restricted to a nice singular set of singular sets for which these cycle count vectors are complete graph invariants. So yeah, these are kind of like the 2 tools that I have for proving my result. Yeah, so I don't think I want to go on anymore in case it drags on for too long. But yeah, I just wanted to thank everyone for coming and see if there's any questions.